Okay, so now we're going to look at another instrument, as I said before, that is used to measure pressure. And the difference between this instrument and the barometer, which we talked about earlier, is that this instrument is used to measure the pressure of a sample of gas, whereas the barometer is used to measure atmospheric pressure. All right, so in this case, if we have a sample of a gas in a container, then this is the instrument that we're going to use to measure the pressure of that gas. Okay, so in this case, the mercury would be the liquid of choice again. And later on, I'm going to explain why mercury is used and not some other liquid. Even though you theoretically could use some other liquid, but mercury is the best liquid when it comes to pressure measurements, all right? So as stated here, the pressure in this case is measured by using the difference in the heights of the mercury or other liquid in the two arms of the manometer. And the reason why it says two arms here is because the manometer, as you can see here, is a U-shaped tube, all right? Now, this particular manometer is called a closed-end manometer because one end here is closed, right? It's sealed, right? The other end is connected to your container, which has a gas, all right? So, if you have the gas here, you open up the stopcock here, the gas flows, and then the gas will exert a pressure on the surface of the mercury on this end of the manometer, and that will push up the mercury level up here in the other end. Based on this arrangement, this situation right here, one can see therefore that the pressure that is exerted by the gas here will be equal to the pressure exerted by the column of mercury on the point here, which is on the same level as the mercury level on the other end, all right? So as a result, we can basically relate the pressure of the gas to the height difference between the two mercury levels on either side of the tube, all right? So basically, the pressure of the gas will be equal to that distance, all right, which is shown here to be equal to delta H, right? So we can actually express the pressure of the gas directly in terms of millimeters of mercury represented by that height difference. Another way of exerting, or I should say of expressing the pressure, is by using this equation here to calculate it if you're trying to get the pressure expressed in pascals, all right? So this is the equation that is used to calculate the pressure in pascals. G is known as the acceleration due to gravity. This is a term that for those of you who will do physics, you're going to understand the importance of that. I won't explain that right now. D is the density of the liquid, which in this case is mercury, expressed specifically in kilograms per meters cube. And I should say also, going back to the G value here, the units of G is expressed in meters per second squared. And H would be basically the height below the surface of the mercury or the liquid expressed in meters. So in this case here, the H here would be the same thing as the delta H here because we're talking about the depth here in relation to the surface of the mercury right here. So if you know what those numbers are, you plug them into this equation, and that will give you the pressure expressed in pascals, all right? So it all depends on how you want to express the pressure. If you want to express the pressure in millimeters mercury, then you just simply measure the distance between these two, and that's it. But if you want to express the pressure in pascals, then this would be the equation that you would use. Okay, so that's a closed-end manometer, but you can also have another type of manometer known as the open-end manometer, which, as the name suggests, has one end open like this to the atmosphere, all right? So basically, that end is open. The other end is still attached to the container, which has a gas. So you have to take into account now, in this particular situation, you have to take into account the fact that the barometric pressure, which is the same thing as the atmospheric pressure, will be acting on the surface of the mercury that is exposed to the open end, right? So that has to be taken into account when it comes to determining the pressure of the gas that is in the container here. So again, one would open up the stopcock here, the gas will flow through, and then the pressure of the gas here will be exerted on this end here, while the barometric pressure will be acting on the surface on the other end here. So obviously in this particular setup, the pressure of the gas would be greater than the barometric pressure because, of course, the pressure of the gas here would be greater to force the mercury level to be higher. So therefore, that tells you that the pressure of the gas here would be greater than the barometric pressure. And the difference between those two pressures would be equal to delta H, right? So basically, we can write down an equation relating the barometric pressure, the pressure of the gas, and delta H, in that the barometric pressure plus delta H would be equal to the pressure of the gas, and that's the equation that is right here. The pressure of the gas is equal to the barometric pressure plus the delta H, the height difference between the two mercury levels on either side of the U-shaped tube. Now, that's what happens in this case where the mercury level here is higher compared to here. If the situation was reversed, as you can see on this side, where the mercury level here is lower compared to the side that is directly connected to the container, then we can again write down a relationship. In this case, the difference between these two values will be equal to delta H, so therefore we can say that the barometric pressure would be equal to the pressure of the gas plus delta H. And that's the equation that we have here, right? So that's basically what we can, how we can calculate the pressure of the gas in the container, if we know what the barometric pressure is, and of course, if we know what delta H is, all right? But you have to be careful when using this equation as opposed to this equation based on the two different situations right here, all right? Now, here we have a question. It says for part B, what is the pressure of the gas if delta H is 100 millimeters and the barometric pressure is 760 millimeters? So therefore, this is the equation we'll be using. So what that means is that we have to rearrange this equation here. We have to rearrange, sorry. What's happening here? Okay. Where is the pointer? Okay, so we have to rearrange this equation here. Okay. We have, oh Lord, what's going on here? All right, we have to rearrange this equation here to solve for the pressure of the gas. So basically, P gas, write it here, P gas would be equal to P bar minus delta H. In fact, let me just go over here and do it over here. So P gas will be equal to P bar, which is 760 millimeters mercury, minus 100 millimeters mercury, and that will be equal to 660 millimeters mercury. All right, and that's basically how that is done. All right, okay, we're gonna stop here. Oh, actually, let me continue to this one. Okay, so this is a very important example because this demonstrates why is it that mercury is the liquid of choice when it comes to instruments such as barometers and manometers. Okay, so this question here, let me see if I can erase some of this stuff here. I guess I can't. Okay, I'm quite sure you can read this anyway. So this question is asking, it says calculate the height of a column of water, and it gives the density of water in grams per cm cube that exerts the same pressure as a column of mercury, and it gives a density in grams per cm cube 760 millimeters high. All right, so what this question is saying is that you have two liquids. They both exert the same pressure, right? And they gave you the height of the column of the mercury, and the question is asking for the height of the column of the water that would exert the same pressure. Now, the equation that you'll be using to solve this problem is this equation which we met before. The pressure is equal to the height times the acceleration due to gravity times the depth or the distance between the surface of the liquid and the point where the pressure is exerted, right? The other thing we're going to write down here is that the pressure exerted by the water column is equal to the pressure exerted by the mercury column, all right? So what I'm going to do, or what I've done here, is write down an expression, actually this expression for both the water and the mercury, and set them equal to each other, right? So the height of the water column times G times the density of the water is equal to the height of the mercury column times G times the density of the mercury column. And then what I would do is cancel out the G's here and here, and basically divide both sides by the density of the water, because what I'm trying to find is the height of the water column. So that simplifies to this equation right here. And then all I have to do from here is plug the numbers in. So the height of the mercury column is 760 millimeters mercury. The density of the mercury is 13.6 grams per cm cube. And the density of the water is 1.00 grams per cm cube. And when I work out all of that, I end up with the answer here being equal to 10,300 millimeters. Let me make sure I include that unit. So the unit here would be millimeters, all right? So, so basically what this question, or what the answer is suggesting, is that in order for you to use water, for example, as the liquid of choice in a barometer, in order for it to measure atmospheric pressure, which is 760 millimeters mercury, then you're going to need a column or a tube which is 10,300 millimeters long, right, or tall, okay? So 10,300 millimeters is basically 10.3 meters. And, you know, just in case you're wondering what that looks like, I don't know if any of you have actually seen me in person, but if you know me, you know that I'm a relatively tall person, and my height is actually 6'5". 6'5" is just under 2 meters, just to give an idea as to what we're talking about here, right? And therefore, what this means is that you're going to need a tube which is 5 times my height if you're going to use water as the liquid of choice for an instrument such as a barometer. And this underscores the reason why mercury is a liquid of choice, because even though water is much cheaper than mercury, the inconvenience of having a much longer tube is not seen as an advantage if you're going to use water, and therefore mercury is a liquid of choice, because in the case of mercury, you need a tube which is at least 760 millimeters high in order for it to be used properly as a barometer. 760 millimeters high is less than a meter, all right? So that's why it's more convenient to use mercury as opposed to water for instruments such as a barometer or a manometer. Okay, we're going to stop here, and the next topic we're going to look at is, well, actually we'll be looking at a series of laws, the first of which will be Boyle's law, all right? Okay, until next time.